Hello everyone, I'm Ronald, your new math technologist. I'm here today to talk about the binomial probability distribution. Are you ready? Let's go. Many experiments are composed of repeated trials whose outcomes can be classified into one of two categories, success or failure. Examples of such experiments are coin tosses and right-wrong quiz answers. The experiments just mentioned are called binomial probability experiment. A binomial probability experiment is made up of repeated trials that possess the following properties. Number one, there are n repeated identical independent trials. Number two, each trial has two possible outcomes, success or failure. Number three, the probability of success equals P, the probability of failure equals Q, and we always have P plus Q equals 1. And the last one, the binomial random variable X is the count of the number of successful trials that occur. X may take on any integer value from 0 to n. In other words, X is a discrete random variable. Now that we know a little bit about the binomial probability distribution, we are ready to look at the binomial probability function. More precisely, this beautiful formula here. We have P of X equals the binomial coefficient times P to the power of X times Q to the power of n minus x for a value of x from 0 to n. Number one, we have P of x is the probability that there will be exactly x successes in n trials. Number two, the binomial coefficient equals n factorial divided by n minus x factorial times x factorial and represents the number of ways that exactly x successes can occur in any trials. To calculate this number, you should be able to see a symbol like that on your calculator. Okay? And number three, P to the power of x is the probability of exactly x successes. And finally, number four, Q to the power of n minus x is the probability that failure will occur on the remaining n minus x trials. Now, we are going to apply what we've learned about binomial experiments to a specific experiment. Consider the situation of drawing 5 cards, one at a time, with replacement, from a well-shuffled deck of playing cards. The drawn card is identified as a diamond or not a diamond. It's returned to the deck is reshuffled, and so on. The random variable x is the number of diamonds observed in the set of 5 drawings. Is this a binomial experiment? To answer this question, we need to verify the 4 properties of a binomial experiment. Number 1, there are 5 repeated drawings. I mean, n equals 5. These individual trials are independent because the drawn card is returned to the deck and the deck is reshuffled before the next drawing. So property number 1 is okay. Number 2, each drawing is a trial and each drawing has 2 outcomes, diamond, or not a diamond, not diamond. So we have only two possible outcomes. Property 2 is okay. Number 3, the probability of diamond equals P equals 13 divided by 52. And the probability of not diamond equals Q equals 39 divided by 52. And we also have P plus Q equals 1. So property 3 is okay. Number 4. X is the number of diamonds recorded, and X can be 0, 1, 2, 3, 4, and 5. So property 4 is also okay. I have another question for you guys. Would you know how to calculate the values for the binomial probability function? To answer this question, we first need to find the binomial probability function. P of x equals the binomial coefficient times p to the power of x times q to the power of n minus x. This gives me p of x equals, my n is equal to 5x, 13 over 52 to the power of x times 39 over 52 to the power of 5 minus x equals the binomial coefficient times 0.25 to the power of x times 0.75 to the power of 5 minus x, for x equals 0, 1, 2, 3, 4, and 5. Now we are going to substitute the values of x into the formula. X equals 0 implies P of 0 equals the binomial coefficient times 0.25 to the power of 0 times 0.75 to the power of 5 equals 0.2373. X equals 1 implies the probability of 1 equals the binomial coefficient times 0.25 to the power of 1 times 0.75 to the power of 4. This is equal to 0.39395, and x equals to implies the probability of 2 equals 5/2 times 0.25 squared times 0.75 cubed equals 0.2637. I have calculated the other values before. X equals 3 implies P of 3 equals 0.0879. X equals 4 implies P of 4 equals 0.0146. The last one, X equals 5, implies the probability of 5 equals 0.001. Note that if we add all these probabilities together, we have 1. Is this expected? Yes, it is. We always have the sum of all probabilities equals 1. The last question for today. What's the most and the least likely number of diamonds that would be observed? This is the easiest question. We just need to look at the probability and decide which one is the biggest and which one is the smallest. So let's do this. I can see that this number is the biggest one. So the most likely value of x is 1. I can also see that this number is the smallest. Thus, the least likely value of x is 5. All right? That's it for today, everybody. I hope you have enjoyed and learned from this video. See you on the next one.